just outside like that. So what's going to change?
The area of the force.
Yes. So now, this is for S less than the radius of the solenoid, which is N. For S greater than N, what is going to change is the flux. So this side is going to be the same, E times 2 pi S. That's going to be the same. Equals to minus P by dt of the flux, which is mu naught N I times 1. What should be the area? Pi, yes, pi A squared. Because outside, it's a long solenoid, so for a long solenoid, you can forget the magnetic field outside here. So that would give you just E equal to mu naught N I, mu naught N pi A squared over, I go the way, squared over 2S di by dt. I'll not take the direction with the minus sign. All right. Now I think we have time to talk about inductance. Okay, so in intro physics to when we study Faraday's law, you remember the induced voltage is related to what we call inductance, right? So the flux, you saw that flux phi equals to L times I, right? And you were told L is called the inductance of an inductor, and it's measured in units of Henry. So you have studied RL circuits, RLC circuits. I think you have done also in Calvin's physics, right? So we will learn the origin of L. So in order to find where L comes from, we just consider two wires. One wire, it carries a current I1, and the second wire, let's assume it carries a current I2. And let's find the flux due to the magnetic field of the first wire through this loop. So all you have to do is just integrate the magnetic field due to this current over this area, right? So let's consider this one is loop 1, and you have another 2, and this carries a current I in that direction, and let's find the flux over this area due to the current flow through this one, I1. So the magnetic flux is the flux through second loop. I can write it phi 2, 1. The flux on 2 due to the field from 1. That's going to be the integral of V1 dotted dA. dA total equals to dA. All right? Now, integration of a vector over the area, like that, we can change it. Well, before we do that, how can we express the magnetic field in terms of the vector potential? If we know, let's say the vector potential that gives us V1 is A1, then what's going to be the form of this? Curl of A1 dotted dA2, right? Now, if you recall Stokes' theorem, you can write this as what? Right? Stokes' theorem, curl and with surface integral can be expressed as the line integral, right? So the curl of A1 over this area, you can write it as y1 is the same as the integral over closed curve 2. Right? A1 dotted dr 2. Just apply Stokes' theorem here. You apply Stokes' theorem, and then you can write that. But how do we express the vector potential? How do we determine the vector potential of a current carrying wire? So we just recall A1 equal to mu naught over 4 pi, the integral over C1 of I1, if it's the steady current, of dL1 over the magnitude of R minus R prime. What's R prime? So we are interested in the magnetic vector potential of just this infinitesimal length dL2. If I put this one is dL2, and if I consider this one is dL1, so I'm interested in the vector potential of the current flowing through this at this point, right? So if I just assume this is the origin, the z, y, x, what I call R prime is this one, right? So this is your R prime. And this is what? This is your R. And this is going to be R minus R prime. So we discussed about this previous chapter. Now, if I substitute this one in here, what would I get? I get pi to 1, which is going to be mu naught I over 4 pi, the integral over a closed curve C2. In place of A1, I just substitute this one. So I have the integral over a closed curve dL1 over magnitude of R minus R prime dotted dL over this one is over C1.